Hello everyone, my name is François-René Lachapelle. I'm an application scientist at PHOTON ETC in Montreal, and I'm here today to talk to you about our deep cool infrared systems. Shortwave infrared solutions are more and more popular these days. SWIR cameras are used for a broad range of applications. For example, in research, it's used for the development of photovoltaic panels or in preclinical imaging of biomarkers in live animals thanks to the near-to biological window. In the industry, it's used for sorting, as in the recycling industry, where it's a great tool for plastic identification. It's also used for quality check processes, like in agri-food and electronic manufacturing, or even in the primary industry for drill core scanning, precision farming, oil and gas leak detection, to name a few. One of the key to this technology is the cooling system. Unlike in the visible, detectors in the infrared market are relying on temperature stabilization and cooling to overcome their inherent dark noise that would otherwise limit their signal to noise and exposure time, and therefore a whole range of applications. In order to properly cool our camera's core, PHOTON ETC uses 4 stages of Peltier thermoelectric cooling and a specific and maintenance-free encapsulation design. This allows to get down to a temperature of -80 degrees Celsius without the hassle of liquid cooling systems or consumable like liquid nitrogen. The SWIR product line offers a eSWIR from 500 nanometers to 1.7 microns in gas camera, and eSWIR MCT all the way to 2.5 microns, or extending even further to 2.9 microns camera. The deep cooling of our cameras opens the way for low-light applications. The SWIR is a broadband imaging system that can be used as a standalone or integrated as a component in our systems or yours. At PHOTON ETC, we also offer a broad range of products integrating our camera, like SWIR, broadband, and hyperspectral microscopes. In SWIR microscopy, we can go to 100-time magnification. The image on the left presents an example of a very faint emission, easily detectable thanks to our camera's high sensitivity. The hotspots are the infrared photonic emission from the activation of transistors in a static RAM and flash memory of a PIC microcontroller. Silicon being transparent in the infrared, this kind of image can be acquired non-intrusively through the backside of the silicon. In-gas photonic emission is a useful tool in IC failure analysis, so very sensitive camera are needed to get good images. Narrowband filtering in wide field imaging also require high sensitivity. For example, a filter SWIR can be used to study new photovoltaic candidates. Electroluminescence, photoluminescence, and reflectance imaging can help identify the presence of defect and rapidly map inhomogeneities. The obtained results contribute to bringing to the market new, cheaper, and easy to process technologies such as perovskite-based solar cells that improve the manufacturing process. In this example, the narrowband filtration is done with a tunable filter. This turns the camera into an hyperspectral imager. Such a photon-starved system would not be possible without a camera with very low noise. PHOTON ETC produces tunable filters with very narrow band and high rejection based on volume Bragg ratings. This can be used for global imaging hyperspectral cameras where neither the sample nor the camera moves. Scanning is done in the wavelength direction. The grandiose system, we call, is a combination of visible and SWIR global hyperspectral imaging with both macro and microscopic capacities. This hyperspectral imaging device is a highly useful characterization tool in photovoltaic research and development, where the peak wavelength of the emission relates to the local physical property of the material. We also couple our SWIR with high throughput reflector spectrograph to do push broom hyperspectral. We call this system LEOs. And these systems use the whole 2D matrix of pixels of our camera to get both the spectral and spatial information at once. And then they scan physically to get the full data cube. This allows to use on a conveyor belt and in an industrial setting, as well as a benchtop installation. The large aperture of these systems combined with the reflective optics, it gives a high throughput. A lot of lights mean fast and efficient scanning. At Photon ETC, we work on a collaborative approach with our clients. This high level of customization and integration capacity of our products is a keystone in our business model. For example, we developed this LEOS push broom scanner for our SWIR cameras, and then we adapted it in a combined array of these LEOs spanning a wide range of spectral bands into a versatile scanning system that can be used, for example, in plastic sorting, agri-food, or mining industry, to name a few. And for the latter, we mounted the scanning conveyor in a commercial container for on-site core scanning, and we provided adapted software solutions. We have this multi-level engineering force for vertical integration to adapt our product to your needs. So another example of customization is the illumination system. It is fundamental and often neglected aspect of SWIR and hyperspectral imaging. We are always working on developing innovative illumination solutions like LED panels, halogen reflector, shape lasers, Bragg filter, tunable laser sources, and etc. Starting from the idea of improving capacities of SWIR cameras through deep cooling, we built around a whole range of optomechanical systems. Photon ETC built a catalog of products through this idea of collaborative approach in high-tech physics and engineering to bring infrared and hyperspectral in innovative markets. Feel free to contact us at info@photonetc.com or go check out our brand new website at photonetc.com.